Welcome to Brain Vision.
Okay, so we're looking at question 28.12. We have two parallel wires that are 5 centimeters apart. So each one is going to be 2.5 centimeters from this point P. And we have currents in each of these wires. The first current is 12 amps going to the right, and then the bottom wire is 24 amps moving to the left. And we're asked to find the magnitude and direction of the magnetic field at point P. So let's first start thinking about the direction of the magnetic field. So looking at the top wire here, we see that the field is pointing to the right, And so using the right-hand rule, if we point our thumb in the direction of the current, then our fingers are going to curl into the page at point P. So the magnetic field is pointing into the page from this top current. From the bottom current, that's moving to the left. Again, if we use the right-hand rule, we point our thumb in the direction to the left, and then our fingers are going to curl into the board. So again, at point P, that's causing a current directly straight into the page. So that's the direction, and that's convenient because it means we're going to be able to simply add the magnitude of the current from of the magnetic field from each of these two wires. So to find the magnetic field from a segment of current, we need to use the Biot-Savart law, which is I've written right up over here. So the magnetic field is going to be mu naught over 4 pi. We know our constant mu naught. And then the current, the segment of length of the wire, and then the sine of the angle. Here, this angle phi, this is the angle that we're going to want. We want the angle between the current and the direction pointing to the point that we want. And then r is going to be the actual distance, so that's going to be our 8 centimeters here. So going through and plugging this in, let's just do this for wire 1. So the top current up here of 12 amps. So copying our equation over here, we have the current in this case is going to be 12 amps. The DL that we want to use, this is the segment, this little red segment, the length is 1.5 millimeters. We need to convert that into meters. That's going to give us 0.0015 meters. And now we need the sine of this angle. So notice that we don't have to actually calculate what this angle is, because we know that the sine of the angle is equal to the opposite side of the triangle that this forms, divided by the hypotenuse of the triangle. So here the opposite side is 2.5 centimeters, or that's really going to be, in this case, 0.025 meters, divided by the hypotenuse, which is 8 centimeters. That's going to be divided by 0.08. And then r is going to be just the distance, which again here is 8 centimeters, or 0.08 meters, and we're going to have to square that. So plugging in all of these numbers and calculating this out should give us 8.79 times 10 to the minus 8 Tesla. So this is the contribution of the magnitude of the magnetic field from just the current in wire 1 up at the top. Now, in theory, we could just do the exact same thing for wire 2 and calculate it. But if we look at the numbers here, we see that the magnitude of the current in wire 2 is twice the magnitude of the current in wire 1. So instead of actually having to calculate the magnetic field all over again, we can just notice that the magnitude of the magnetic field, since all the other numbers are the same, is just going to be exactly the same. So we are just going to double this number and add it to itself, because the double value of this number is going to be the magnitude of the current of the magnetic field from the current in wire 2. So when we double that number and add it to itself, we get that the total magnetic field here is 2.64 times 10 to the exactly minus 7 Tesla. And again, this is into the page as we determined.